Welcome back to Calculus, and we are going to explore what a derivative means with regards to a graph. So I have two graphs here, f of x on the left, g of x on the right. Let's look at what the derivative means. So derivative is the slope of the tangent at any given point. So let's draw in a bunch of tangents here. So pretend that these are all tangent, but envision that those little red segments I drew are all tangent to the curve. The slopes of all those tangents are negative. So over here, the first derivative is less than 0. And notice that our curve is going down. Our curve is decreasing on that interval where the first derivative is negative. On the other side, if I draw a bunch of tangents, here, all of those tangents have a positive slope. And notice those green positive slope tangents are on the side of the curve where the curve is increasing. Now, what happens at the vertex of this parabola, if it indeed is a parabola, right here? What kind of tangent is there there? Well, right there at that minimum point, the tangent is horizontal, meaning the derivative, the slope at that particular value is equal to 0. Now, with g of x, it so happens that no matter where I draw my tangent, almost, the slopes are always negative. And all of these things, all of these tangents have a negative slope, and this curve is decreasing for all of these values of x. But what about right here where it's crossing the origin? What's going on there? If we were able to get in real close, we would see that actually at that instant we have a horizontal tangent. We have that instance on the graph where as we get infinitely close to that point, these tangents are getting flatter and flatter and flatter and flatter and flatter, so at that point the tangent is actually equal to 0. This graph, we have a minimum. This graph, we have what's called a point of inflection. A point of inflection is a point where the graph changes its curvature, where it's changing from being concave up, there's concave up, to concave down. At this blue point that I have drawn on g of x, our curve has changed from being an upward-facing cup to being a downward-facing cup. So let's summarize what we just observed. Hopefully you observed the same things that I have. But if f prime of x equals 0, then f will have what at x equals a? Well, it's either going to have a maximum, a minimum, or a point of inflection. If the first derivative is positive, then f of x is increasing. And if f of x is less than 0, then f of x is decreasing. To go a step further and introduce the second derivative, if the first derivative is equal to 0, and the second derivative is positive, in other words, it's concave up, then x equals a is a local minimum. I should say this is f of a is greater than 0. If f prime of a is equal to 0 and f double prime of the second derivative at that point is less than 0, then x equals a is a local maximum. Cool. Nifty. There's a nice little summary for us. Let's use it. Find the maximum and minimum points on this curve. All right, so what do we do? Let's find the derivative. Y prime is going to be 8x cubed minus 4x. If I'm looking for maximums and minimums, I want to know where this derivative is equal to 0. I want to know where on this graph will the tangent be horizontal. That's what this is finding. That's what this says. So we solve this. So this is factorable. And that should be an 8. So this is x squared minus 1 equals 0. So x equals 0, x equals 1, x equals negative 1 are possibilities for maximums and minimums. These are what we call critical points or stationary points. Now what we need to do is we need to determine if they are indeed maximums or minimums or points of inflection. And to do that we can use what's called a sign diagram. I'm going to label those critical points on this number line. This is just a number line. And then I'm going to test numbers in each interval. So let's take a number like negative 2. If I substitute negative 2 in to the derivative, f prime of negative 2 is less than 0. And what does that mean? That means this is decreasing. If I take f prime of 1/2 and substitute that into my derivative, I'm positive, so that means I'm now increasing. So what I've just figured out is that at x equals negative 1, since I'm going from decreasing to increasing, at x equals negative 1, there is a minimum, not a maximum. And then let's test a number between 0 and 1. F prime of 1/2. Substituting that value into our derivative, we get that that's less than 0. I don't care what the number is, I just care that it's decreasing from 0 to 1. And if I substitute 2, f prime of 2 is greater than 0, so I'm increasing again. So we're decreasing on that interval, increasing on that interval. So at x equals 0, there is a maximum. And at x equals negative 1, positive 1, there is a minimum. So this graph has 2 minimums and 2 maximums. And hypothetically, what would it mean if it was decreasing between 0 and 1 and then decreasing from 1 out to infinity? Well, that means it can't be a minimum or maximum. It keeps going through that point. That's going to be where we have a point of inflection. Good stuff. Now, if it actually said to find the ordered pairs, we would want to substitute these 3 values into the function and find the coordinates of those points.